Good morning guys, Anjani Kumar here, dealing instrumentation subject for final year electrical students. Alright, in the last session we discussed about the resistive transducer. Alright, we discussed about what is the operation, what is the working principle of a resistive transducer, and what is the formula that we'll get in a resistive transducer, and different types of resistive transducers, right? What are the examples, right? Position, displacement, Wheatstone bridge based, and moreover important concept that we discussed, resistive temperature detector or TD, how the temperature, non-electrical quantity like a temperature, how you can find the temperature with the help of resistive temperature detector that we discussed. And what are the advantages and disadvantages of resistive transducers, and after that applications that we discussed up to now, right? I just want to give a brief rewind about all the resistive transducer. So what is a resistive transducer? Which finds the non-electrical quantity by changing the resistance itself. So that type of transducer we can call it as a resistive transducer. So right, you know the resistance is equal to rho L by N. So if you change the length, you will get the change in the resistance. If you change the resistivity, you will get the change in the resistance. You will change the conductor cross-sectional area, you will get the change in resistance now. So in this way, these are non-electrical quantities. So what is the L is nothing but a displacement. Rho is nothing but resistivity. We don't have any meters. We don't have any instruments to find the resistivity, displacement, flow meter, right? Positions, and all these things. That's why we require transducers to find this one. So if you change the resistance, if the change in resistance, you can easily find out the calibrated scale itself, right? So with help, these are the things, these are the different categories that we need to find the changing resistance, right? So these are the non-electrical quantity which can be converted to electrical quantity. So, and what are the different examples that we discussed? That is nothing but displacement transducer. For suppose if I have a resistance here, the sliding contact here, the voltage that you are giving, the voltage which is a voltmeter. So you are changing the sliding, means if the sliding here, the displacement just you need to measure. So it's very difficult without we don't have any instrument to find out the displacement, right? How much displacement that you are doing in this circuit. That means, so whatever the displacement is, there is a changing resistance. For suppose if it is R1, when you create a displacement, the change in resistance is R2. There will be a changing resistance. Now you know the calibrated scale, you will find out the voltmeter here, whatever the voltage here, that is equivalent to the displacement itself. So that means the displacement which is converted to the voltage itself, right? After that we discussed about the Wheatstone bridge, how the Wheatstone bridge is working, means what is the formula? R1, R2, R3. So passive transducer means it requires external supply, then only these type of transducers will work, right? This is a null deflection, right? So when R1, R3 is equal to R2, R4, then only the bridge will be balanced. It will show the zero deflection, 0 volts here. So if you want to find out the temperature that can be applied across this resistance, so what happened? Your null deflection will vary now. So this formula is violated now. Your null deflection will show 2 volts, right? So how the 2 volts, which is analogous to the change in temperature, right? My temperature which is converted to electrical signal. So the temperature non-electrical quantity which is converted to electrical quantity, we can call it as a resistive, we can call it as a change in resistance, right? We can call it as a resistive transducer, Wheatstone bridge type of resistive transducer. And after that we discussed about RTD. RTD is nothing but resistive temperature detector. It can find the temperature by measuring the changing the resistance itself. So these type of transducers, our working principle is nothing but by changing the resistance. If you measure the changing resistance by applying the temperature, by applying the temperature, you can find the non-electrical quantity which is equal to the temperature. We can easily find out, right? How it will work means it is having a metal. What type of metal? We can go as a platinum metal. Why we are going for platinum metal means which is a positive temperature coefficient. That means whatever the temperature increases, your resistance is going to be increases. Right, there is a semiconductor materials also there are negative temperature case. We need not go for this one. If that means if the resistance is reduced, means you can get a difficulty while finding the changing resistance, right? So that's why you always prefer for a platinum metal or a conducting metals that can be used for finding the temperature itself, right? So how it will work means, whenever the temperature that is applied to that metal, what happened, the metal resistance will change. So the change in resistance we can calibrate it with a scale, so that is analogous to the voltage that are generated from the changing resistance, which is analogous to the temperature. So in this we can easily find out the temperature. We discussed in detail in a last session. After that we discussed about the advantages of resistive transducers. So what are the advantages? The cost is very less, right? These are very quick and these are accurate results that you'll get. After that, different sizes, these are available at different sizes, from the small size to big size, right? So it can be used any other circuit if those type of transducers are not required also. So these are the advantages of a resistive transducer. And what are the disadvantages of resistive transducer? The sliding wire is there, it requires a more power, right? More power, and there will be a noise will be generated across the slide when moving the sliding wires across the resistance, right? What are the applications? Means temperature detector, strain detector, pressure detector, displacement detector, resistivity detector, right? All these things that we discussed. And what are the properties of a metal? What is the properties of a metal while choosing in a resistive transducer? Also we discussed, right? These are the things that we discussed in our last session. I hope it's clear about all the information regarding resistive temperature, resistive transducers, right? Now we'll move to the another concept which is not that much important, but you have to know the idea of second category of a passive transducer. So that is called inductive transducer. It's inductive transducer. So it is also one of the part of a passive transducer. So why we can call it as a passive transducer means these type of transducers that require external electrical supply for its operation. Right? So that's why these type of transducers that we are calling passive transducer. Right? So the inductive transducer. Now in this we'll discuss about what is the working principle of inductive transducer. Right? Working principle and different types of inductive transducers. And after that some real life applications. Right? So we don't have that much concepts in this type of inductive transducer, right? Now we'll discuss about working principle. You will tell working principle, right? You can find your unknown quantity, non-electrical quantity, right? Which can be found by measuring the change in the inductance. In a resistive transducer, you can find your non-electrical quantity by measuring the change in the resistance, right? In the case of inductive transducer, you can find your non-electrical quantity by measuring the change in the inductance itself, right? So we can find the non-electrical quantity by measuring the change in the inductance, right? So this is the working principle of an inductive transducer, right? So how it will work means, for suppose if you apply whatever it may be, you don't know the non-electrical quantity. For suppose if you want to find out the motion, right? So that you applied, so what is the position motion? It's a motion that you applied. Right? So how the inductance changes means, the first it will convert it to change in flux. Right? After that it will convert it to change in inductance, or flux linkages, whatever it may be, the motion that you are applying, right? The motion which is converted to change in flux. Directly there is no contact, there is no conversion of change in inductance. If you want to find the change in inductance, means you require a change in flux, right? Whatever the non-electrical quantity which is converted to change in flux first. If the change in flux is happened, the inductance will be changed. So these inductance we can calibrate it, right? You have a voltmeter or ammeter which is connected to this change in inductance. You can find whatever the variations that you will get. So whatever the output voltage, voltmeter or ammeter, you just connected across the inductor. So whatever the output changing voltage which is analogous to the whatever the motion that you applied. So is there any direct device which is used to find the motion of an instrument or a displacement of that instrument? We just need these type of inductive transducer, right? So whatever the motion which is analogous to the change in inductance, let's remember change in inductance with the help of a voltmeter that you connected across the inductor, right? So I hope it clear. I think nothing is there. Whatever the motion, you need to find your non-electrical quantity which is converted to electrical quantity, right? You just first it will convert the change in flux. So then change in flux happen means it's obviously change in inductance will be present. So inductance nu em chestunnao voltmeter connect chesi enta inductance change ayindo find out chestunnao. So aa inductance enta change ayindi depends on enta motion that you are applied, right? So that my motion which is equal to the output voltage, right? Non-electrical quantity which is converted to electrical quantity. That's it. So this is a working principle of a inductive transducer. Nothing is there. So while measuring your non-electrical quantity, how you are measuring means by changing the inductance itself. So before the changing inductance happens, the changing flux will be created, right? So that is a simple concept that you are going to understand, right? So this is a working principle of a inductive transducer. So before going to the types of inductive transducer, first you know what is a self-inductance and a mutual inductance, right? What is a self and mutual inductance? Right? So what is a self-inductance? Self-inductance means whatever the, if you applied a, right, if you apply a voltage across the inductor, the current will flow. Whenever the current will flow according to the Ampere's law, what happened? There will be a flux will be generated. This is a twisted conductor means there is a change in flux will be created. If the change in flux is created, the voltage will be generated. That means whatever the flux created in this coil, the voltage also generated in this coil itself. So these type of EMF, these type of inductance, we can call it as a self-inductance, right? No voltage apply chesavu, current will indi, so thereby a flux will be generated. There will be a change in inductance will be generated. So the inductance that is developed, that is generated by the coil itself, so that we can call it as a self-inductance or a self-induced EMF. The voltage that is generated across the self-inductance coil, we can call it as a self-induced EMF, right? But suppose I have one more coil, right? So these are magnetically coupled, right? So magnetically coupled. If you voltage applied, flux will be generated, current will be flow, there will be a flux will be generated. These are magnetically coupled. That means there will be a magnetic coupling. So these flux will be travel here. So these flux will be travel here. That means here also we are getting the flux now. Thereby some current will flow now. Thereby some voltage will be developed now. So these type of voltage we can call it as a mutually induced voltage. Clear? The flux in one coil generated the voltage on another coil. So that is called a mutually induced voltage. So these are the basic things we need to understand. I hope I don't want to go for a large session for this. Nothing is there. If the inductance that is developed in itself, right? So whatever the voltage that you applied this coil, the current will flow, the flux will be generated, there will be a change in flux is generated, there will be a change in inductance will be created. That inductance in that coil we can call it as a self-inductance, right? If the voltage that is generated in itself, that means in the coil itself, then we can call it as a self-induced EMF, right? We have two coils which are magnetically coupled. That means whenever the voltage is applied in one coil, the flux will be generated. These flux will be linked with another coil. There will be here also change in flux is there. There will be a change in inductance also present. These type of inductance in this coil we can call it as a mutually induced EMF. So thereby the voltage that are developed across this coil we can call it as a mutually induced voltage, right? We don't have any voltage here. Whenever you applied a voltage, these flux created the voltage here. So that's why we can call it as a mutually induced voltage. The flux we can call it as a mutual flux. So its self flux we can denote it by L, mutual flux we can denote it by M. So these are the basic things we just understand, right? And we'll start at different types of so always we should go apply a alternating current to inductor. Why? So if a DC supply is applied to the inductor, what happened? Alright, but suppose if the inductor is here, if you apply a DC supply, so what happened? So what is the voltage across the inductor? No problem. Whenever you apply voltage, the current will be flow. Then there will be a flux will be generated. These are twisted conductor, means there is a change in flux. According to the Faraday's law, change in flux will produce the EMF, right? Voltage will be generated. So what is the formula for voltage? V is equal to L di by dt, right? You are applying a what type of voltage? This is a DC voltage. That means whatever the current, that is a DC current. If a current is constant, means the differentiation of the constant, what happened? The voltage is equal to 0. If the voltage is equal to 0, so what happened? Voltage equal to 0 is nothing but short circuit, right? So that means if you apply a DC voltage, DC supply to the inductor will get short circuit. So that is one of the important questions that we need to understand. Alright, so what is a short circuit means? Short circuit means this we can call it as a short circuit. So what about the resistance? Resistance is 0. If resistance is 0, what is the voltage? 0. If it is an open circuit, means this is the open circuit. That means there is no current will be flow. Current will be 0. If it's open, what about R is equal to infinity? So we need, these are the basic things we need to understand, right? Right? Why the inductor doesn't allow sudden change in currents, right? So this is the same. V is equal to L di by dt, na? Right? Sudden change, it doesn't allow sudden change in current. What about the time? Time value is very less, small, so it should almost equal to 0. That means if it is 0, what is the V? V is equal to infinity. That means infinity voltage will appear across the inductor. So that way inductor doesn't allow sudden change in current. It will take time to change from 1 amperes to 2 amperes, whatever it may be, right? So these are the basic things we need to understand while discussing about the inductance, right? So what is the self-inductance? What is the mutual inductance? What is the voltage across inductor? Why we can't apply a DC supply to a inductor? These are the basic things for each and every person should know. Alright. Now we will discuss about types of a transducer. There are two types of a transducers, right? Two types of inductive transducer. So one is single coil inductive transducer. That means we can call it as a self-inductive transducer. Single coil is present in the self-inductance. The coil itself, the inductance developed in the coil itself, right? Self-inductive transducer, right? And the second one is mutual. That means two coil inductive transducer. So we also call it mutual inductance, mutual inductive transducers, right? Now we'll discuss about single coil inductive transducer. Nothing is there, simple in construction, simple in logic. So logic is nothing but if you want to find out the motion or a non-electrical quantity, that can be measured by changing the inductance itself, right? That is the concept. So first we can call it as a single coil or a self-inductive. That means how it will be look like means see, nothing is there. This is also a magnet. Nothing is there. This is a single coil inductive type transducer, which is having a single coil. That means this is having a two magnets. So one is this is one magnet, right, which is having a two magnets. So these two magnets are connected like a parallel. Right, so one magnet which is having a coil which is connected like this, one coil which is connected to one magnet, and another magnet, this is nothing but this magnet we can call it as an armature, right? So we just think it up. This is another magnet which we can call it as look like an armature, right? One magnet, one coil is going to be connected here. The coil is excited by the AC supply, not a DC supply, right? Coil is excited by the DC supply, and this is a meter, right? So how much inductance? The meter will specify the voltage or current of that inductance, right? But suppose now you have to apply the motion here. So if you want to find out the position or a motion that you need to find out, right? So when you apply a motion, this is the air gap now, right? So when you apply a motion, this magnet will move like this. Right, so then that means what happened? The air gap will be changed. When the air gap will be changed, that means the change in flux will be created, isn't it? But suppose if the magnet is here now, if you move like this, whatever the flux here, so per suppose in this position, at this position you have a 40 flux, right? So when you move this magnet upwards, what happened? The air gap will be changed now. That means the change in flux also generated now. So the flux is 50 flux. That means you are changing flux. If the change in flux happens, the inductance also changes. Right? How much amount of inductance changes, that can be find out the meter itself. Right? Whatever the output of a meter, which is analogous to the motion that you applied. That means whenever the air gap change means the distance will be changes. If the distance will be changed means the flux will be, if the two coils which are very nearer, so what happened? The flux will be easily generated, easily transferred. Right? If the two coils are very far away, it will take time. So the change in flux will be generated, right? I hope it's clear. Nothing is there. We have a two magnets which are connected in parallel. One magnet which the coil is connected through a meter and through an exciter. The coil is excited, there will be a flux will be generated here. Right? Whenever the coil excited means there will be a flux generated, right? Another magnet is connected in parallel, right? So whatever the motion that you need to find out, that can be applied across this magnet. So what happened? If the motion you applied, that means the change in air gap will be changed. Whenever the change in air gap, that means the change in flux will be generated. So the change in flux means change in inductance will be created. So these inductance can be calibrated the scale over here. So whatever the output of the scale which is equal to the motion, that means whatever the motion which is converted to voltage or current, whatever it may be, voltage, whatever the meter. If you take the voltmeter, the voltage, if it is a current meter, that is ammeter, that is a current, right? The motion, which is a non-electrical quantity, which is converted to electrical quantity. So that's why we can call it as an inductive transducer. So you are converting the motion into change in the inductance. So what is the parameter here? The change in inductance, right? So this is a single coil inductive transducer. Nothing is that simple in construction, right? We go for two coil. Two coil is nothing but mutual inductance. How you can calculate it, we'll see. Two coil inductive transducer. Right? We'll see how the functioning will be. Similarly, the same thing. You have a two magnets which are connected in parallel. Another magnet you are placing here. Right. In this you are placing a coil. The coil is excited by the AC supply. Right. So these are the flux. And we are having another coil. Right. The name itself indicates this we can call it as air gap. This we can call it exciter. So we place a meter here. Like similarly. So the motion that you are applied here. So if you want to find out the motion, here there are two magnets, but we are having a two coil. Only one coil is going to be excited by the AC supply. Right? Another coil we are taking the output meter. Right? Now whatever the motion that you want to find out, that can be applied here. So when a motion applied, this magnet will move. That means the air gap will be changed. Whenever the air gap will be changed, here the change in flux will be created. So that means here the change in flux will be created. This change in flux will move to the another coil, will produce as the flux. Another flux is here, right? This is called a mutual inductance. So this change in flux, the change in flux is here, will move like this and created the voltage here, right? These voltage we can find out the meter itself. So whatever the output of a second coil, which is analogous to the motion that you applied. See, once again I am telling, right? When you applied a motion, what happened? The air gap will be changed. So when air gap changes, the change in flux will be created. See, in a first we have a 4 flux at this position. When you apply a motion, the air gap will be changed. The change in flux will be created. The change in flux will be 50. Right? The flux which is magnetically coupled, na? These two coils are magnetically coupled, right? These flux will travel like this and moves here. Here also change flux is there, na? Due to that flux, some voltage will be generated, na? So whatever the voltage that you are getting in the meter itself, that voltage which is equal to the motion that you applied. Right? So these type of that means the motion which is converted to the voltage. So that means what we can call it as a transducer. Right? So this type of a transducer we can call it as a two coil inductive transducer. Similarly, nothing is there. In a last figure, the one coil is going to be present. In this, there are two coils are going to be present. So that's why we can call it as a two coil transducer. That's a single coil transducer, right? When you apply a motion, air gap will be changed, the change in flux will be created. This flux links with this coil and produces the voltage. The voltage is here. Deni valana voltage vastundi when you apply a motion. That means the motion which is equal to the output voltage. That directly you will say the motion which is converted to voltage. So that is nothing but it's a transducer, inductive transducer. So these are the different categories of transducer that in inductive transducer. And what are the applications? There is no advantages and disadvantages. Each and every machines that we require these type of inductance present in the system, and that's why we don't have that much advantages and disadvantages of this type of inductive transducer. But we have some applications, right? So you can be used in a position sensor, right? Position sensor. So position, if you want to, for a particular position, there is a change in flux, there is a voltage. The voltage which is equal to that position. Change the position, find out the voltage. How much position change, that much voltage is generated, like. And dynamic motion. We discussed dynamic motion. The motion of the instrument also we can detect with the help of these type of inductive transducer. and this can be used in indicating type instrument, indicating places where we need to indicate some voltage, we need to change the air gap and all these things. So these are the application that we used in inductive type of transducer. So this is about inductive type of transducer. And so what is the working principle of inductive transducer means? If you want to find out your unknown quantity, that means non-electrical quantity, which is measured by measuring the changing the inductance, that's it, nothing is there. Different types of inductive transducers means there are two types of inductive transducer, single coil and two coil type inductive transducer. Single coil type means while changing the motion of another magnet, what happens, air gap will be changed. Due to that air gap changes, there will be a flux changes. Whenever the flux changes, the inductance will be changes. The change inductance that can be calibrated by the scale, and whatever the output of the scale, which is analogous to the motion that you are applied. That means the motion which is converted to electrical, that's it. And two types, two coil type means there are two coils which are magnetically coupled, another magnet is connected in parallel. When you apply a motion, the change in flux in one coil which is coupled to the another coil. So what happened, that means that the voltage that will be developed in another coil itself. So whatever the voltage are developed at the another coil, which is analogous to the motion that you apply, it's like a mutually coupled, right? That's it. And what are the application? That is nothing but it can be used in a position sensors and dynamic motion calculators, right? And indicating type instruments. So these are the real life examples that we are going to use in these type of transducers. So it's about inductive type transducer, and in the next class we discussed about a capacitive transducer, which are more very important concept. Thank you for now.